from essentially every psychiatric disorder using fMRI data as well as clinical features. And a really exciting project right now that's actually looking at speech information to try to get insights for what's going on in the patient's mind. In addition, there's also some other foundational work that's very relevant, especially to medical informatics, counterfactual reasoning, how to use observational data, so not RCT data, to try to learn individual treatment effects by thinking about the counterfactual outcomes that might happen, as well as issues that come from combining data sets from many different locations, many hospitals, ideas like covariate shift, as well as batch effects. It's very relevant for medical applications from many different venues, locations. And my current passion is this idea of survival prediction. That's today's topic. So let me start by describing the actual task we're looking at. I talked to many people looking at end-stage liver failure, and their question was, should a patient with end-stage liver failure be waitlisted for a new liver? And the answer they said was yes, but only in certain conditions. If the patient has a 95% chance of surviving at least 3 months with a new liver, and also an 85% chance of surviving at least 5 years, and some other time constraints. Otherwise, it might be not worth giving this liver to a patient, but to another patient. So that's the waitlisting decision. And to do this, of course, you need some way to estimate the relevant statistics. What the chance of this particular patient, X, will survive at least a certain amount of time for different time points. So how do you do this? Well, so let me ask, could you use the standard models for survival prediction analysis? And to give a context, imagine this horrible situation that you've learned that you have potentially fatal disease. What's your first question? And again, if I had an audience here, I'd ask people to raise their hands, but it's too complicated. Let me fill in what other people have said. What can I do to reduce my risk to live longer? That's a question that makes sense. What's the probability I'm going to survive at least 10 years? I like that. That's a good question. Other people like me have had this disease. What's their 3-month survival probability, or 1 year, or 5 years? But the question most people would ask is none of these, but actually is, how long do I have to live? What's my personal survival chance or distribution? Turns out there are lots of tools for answering these specific questions. So for first one, there's something called risk analysis. So for every patient with his or her covariates, you get a risk score. And of course, high risk is bad. You want to have a low risk. That means a long survival. So to do that, there are tools that, for example, there's disease risk index. So for example, there's a tool on the website, as about lung cancer, for example. And actually 10 features, 10 sequentially, and gives you a risk score. And it says, well, there you are. The best you, given who you are, could do is over here. And there's your risk. And look how pretty the colors are, right? You get an idea. This is the best situation, and you're up here. And now maybe if you go to the gym more often, you stop smoking or whatever else, you can reduce your risk. That's great. But if I reduce my risk from there to there, what does that actually mean? Will I live another 30 years or the 2 weeks? This risk score just says living longer, but isn't calibrated in any sense. I would argue it'd be more relevant, more interesting to say, not just it's better to be here, but how much better to quantify it. So I want to calibrate its score. So that's another question. Here's again a sample. You can ask for survival probability at 10 years, for example. And here you could ask about these people, give scores. Again, high survival probability is good. You want to have a high chance of living 10 years. Oh, that makes sense. So there are tools that are also the famous Framingham study, like the cardiovascular disease. And here I asked about 7 features. At the end of this, it gives a risk, a 10-year risk. And it says, that's your 10-year risk. There's 22.9% chance of this individual living 10 years from now. And that's great. That's useful information. That's calibratable information. But why 10 years? Why not 1 year? Why not 20 years? Well, that's too bad. So what about giving a survival curve? Probability of survival at each time. So here the game typically is, let's find different subgroups of patients. So for example, males with box score of 4 and give a score for those people, and females with box score 2 and give a score for those people. And now this is a Kaplan-Meier curve, which is basically saying, well, I'll say more about that in just a second. So there are tools which do this online. There's a famous SEER, surveillance, epidemiology, and end results data set. You put in certain characteristics. So like, I can help you, boss. This is a survival curve. This is a Kaplan-Meier curve that says for every time, the chance of living at least this long. So you can look up at this curve and say, the chance of surviving at least 5 years is 11%, and 10 years is 7%. So that's great. I can look at multiple time points and give survival probabilities at 5 years, at 10 years, at 3 months. But this curve applies to everyone. It applies to everyone with lung and bronchus cancer, 65 years old plus, and male. But it ignores histology and blood work. It ignores SNPs, single nucleotide polymorphism data, or maybe comorbidities and other diseases that might be present. So that's not everything you'd like, not in this days of patient-specific treatment. So back to the first question I asked, there are tools which do that. There are risk scores, there are one-time survival probabilities, and there's population-based survival curves. But how long do I have to live is a question most people really care about. How can you do that? Well, imagine I get the same set of people. Imagine I could give a curve for every person. This is a curve for one person, another person, a third person. And from that, I can produce, for example, the mean value, the expected value, how long someone has to live from this curve or this curve, that curve. And again, I want larger numbers. So this would be nice if we can do it. But gee, you say, but isn't that the same as the population survival curve? It's not. We actually looked at stage 4 stomach cancer, and we had, I think 128 different subjects with stage 4 stomach cancer. And I didn't show here that we have a Kaplan-Meier curve, which shows the median survival time is 11 months for these people. But now here are 2 of these individuals with stage 4 stomach cancer. And we have 35 other characteristics, including these 3 blood factors, as well as other things. And now we can build different curves for these different people. Mr. 1314, there's the 11-month, the Kaplan-Meier curve for the population set for stage 4 stomach cancer. He's going to live twice as long. You can probably see his son's wedding next year. That's the good news. Unfortunately, Miss 1523, here's her survival curve. There's 11 months. She lives a fifth as long as the Kaplan-Meier population would say. She probably should be in a hospice right now, given less than 3 months. So it can make very big difference depending on other factors. So that was the motivation. I'm now going to do a sort of survival analysis. Oops. I'm not sure why my animation is not doing a good job. Okay. Okay. Sorry about that. So I'm going to give a survival analysis 101. And again, I apologize to the epidemiologists in the room who already know all this stuff. I'm going to say what survival analysis is, and the critical word is the word censoring. I'll talk about what that means. Talk about Kaplan-Meier curves in a little more detail. I'll skip the hazard function, talk about survival prediction versus survival analysis, talk about our task. That will segue naturally into a tool we developed, this multi-task logistic regression model, as well as this interesting novel way to evaluate them. I'll talk about empirical evaluations in terms of decalibration, as well as other more traditional calibration knowledge, and have discussions. And again, for people with background survival analysis, this will be a little boring for the next few minutes, but bear with me. Okay, keep going. I'll keep going. So I should also mention, while the focus is time to death, survival models are very general. They're time to remission, or time to relapse, or time to re-injury. Or maybe in non-medical sense, you've got a part. What's the time until this part in a factory will fail? Or the time until someone gets promoted in a job. And the famous customer churn, how the time until a customer stops going back to Safeway. And these are all time until an event. So this analysis applies to all of these. And my favorite example, time until a student graduates, but we'll talk about that later on. Okay, so here we go. I'm going to talk about what survival analysis is. I'm going to start by talking about a survival data set. So it looks like this. You've got a bunch of, every row is a person, an individual. Every column is a characteristic, age and sex and KI67 and BMI and things like that. And there's also this dependent term, the time. And so what do you do with such data? Well, one thing you do is find risk factors. And a lot of survival analysis is doing that and saying, being male protects you. God, I'm not sure. Protects you against this. Means you live longer if you're male. Or having a high BMI increases your risk. That means you die faster with it. So a lot of analysis just looks at features, and this feature has a characteristic that's relevant. But another thing you can do with it is do something like a regressor. I want to tell you for a novel patient what happens to that individual. And that's where my interest is, building regressive models for novel patients. So it looks just like regression. I've got a bunch of covariates and I want to predict a non-negative value. Done. Why this spiel about this hard thing? Why is it different to regression? And the answer is this bit in the end, the sensor bit or the sensor value. What does that mean? Let's go through an example. Imagine we had a study that started in 1990, a 5-year study. And over this time, people enter the study, and some people, unfortunately, don't make it out, right? They pass on. And they might come at a midpoint and pass on. These are familiar. These are cases where we know the outcome. But there's some patients who, after 5 years, study's over, they leave. They're lost to follow-up. We know they lived at least 5 years. They might have lived 30 years, or maybe they died the next day. We don't know, and we never will. Other patients may leave the study in the middle, and they move to Saskatchewan, some obscure location like that, or whatever. So this is what censoring is. So these patients are uncensored. These ones are so-called Wright censored patients. Excuse me. And that's what that bit is. This is a censor bit. Some patients are uncensored. We know that this person lived 3.1 years, this person lived 2.2 years, but the other patients are Wright censored. They lived at least 5, at least 3.9 and so forth years. So again, to be precise, the censor bit is 1 if the time of death of that patient is equal to the time we record. And it's 0, it's just backwards, I know, if it's a lower bound. So this data, all these individuals here, you can't just ignore them. They've got information. There's not nothing. We know a lot about them, at least 5 years, at least 3.9 years. When I first started looking at survival data, I thought, just ignore them, right? There are only a few of them. Wrong. Many data sets have 70 or 80% censored. If I throw away 80% of my data, I am losing a lot. That's clearly the wrong thing to do. So you need to have a whole body of technologies that aren't just regression to handle these puppies. What are some tools? Well, I've already talked about some of them. You can look for a fixed population of patients. You're going to find a survival function. This is the chance of living at least T months. And this is 1 minus the cumulative distribution function. Why is it 1 minus? Who knows? But so if you know what a CDF is, this is 1 minus that. Okay. So this patient has a 50% chance of living these 12 months and so forth. So Kaplan-Meier, I think in the late 50s, had this way of building a piecewise constant curve like this one here for a population. And you can do some comparisons like male versus female or drug versus placebo. And you get survival curves. Just to track if people are following. Given these statistics, would you rather take the drug or placebo? Do you guys have show of hands, right? How many people would say the drug, I want to take the drug given this survival? How many people think the placebo? Equally silent both ways, okay. Yeah, so clearly here, the placebo is a good idea. Good, thanks, Bill. And there are things like log rank tests to see whether the two curves are significantly different, well, like a chi-square or t-test or something to say there's a difference. This particular feature made a difference. This is that survival analysis routine where you're trying to figure out, did it make a difference? You can find risk factors. Good, okay. So it's good for survival analysis, perhaps, but as I showed earlier, this for a whole population and ignores all the covariates, all the factors. It wasn't designed to answer questions about individual patients. Okay. So again, this is where I already saw these points already. So that's one body of tools. There's also hazard functions, which is another cute. So survival is a chance of living a certain length of time. Hazard is, suppose I live this long, what's the chance I die the next instant? So this is the rate of change. It has this, so for example, after surgery, it might be a high rate of death 6 months after surgery. But if you've lived 24 months, the chance of dying is not that big. And in case you're curious, the survival function is obviously the exponential of the negative integral of this function. So all that's pretty obvious. So there's a lot of things you can do with hazard function. There's Cox proportional hazard, which I'm going to skip right now. But there's a lot of tools that they've built for that. And again, and there's many things. There's Cox proportional hazard model, and there's elastic net extensions to this, and there's random survival forests and prognostic scores that are trying to give populations, and there's single time probability estimators like Framingham, the Gale model. And these are things like a censored version of support vector regression, a bunch of tools. Oh, other questions? Okay. So again, survival analysis is really important, finding prognostic factors and treatment efficacy, the focus on population-based values. And if I have a new drug or new medical device, I use a Kaplan-Meier curve to help the population in general. Great stuff, keep doing it. My interest is on this side, survival prediction. I want to build a patient-specific survival time or risk or something. An MLTR, the test I'll show about in a moment, risk scores and prognostic scores are individual. You value for individuals, and that can help for treating or managing individual patients. So different tools, but very relevant tools. And both are useful, but I'm on this side of the spectrum. So back to the task I motivated. Should a patient get a certain procedure, like a liver transplant or expensive drug? And the answer is yes, but now certain conditions, 95% chance of living 3 months, 85 for 5 years, yada, yada, yada. So I need to reliably, this is just a repeat from earlier. So how can I do this? Well, I need to reliably estimate for a given patient time this probability multiple times. Should I use a risk assessment tools like the Cox proportional hazard gives me a number? No, I want a probability, not a risk score. And it needs to be different at different times. Yeah, there are time-specific hazards, but even that's not a probability. This is the wrong tool for my problem. What about a group multi-time probability to map every patient to like Kaplan-Meier? No, I want to individuate. I already showed that there are different characteristics for different people, even from the same subpopulation. So that doesn't work either. Maybe I should use individual time points, build one model for 3 months, one model for 5 years, one model for 10 years. Well, I could do this because that is a problem. What if these different models say, for example, suppose a model, the first model for the 1 year prediction says no chance of surviving more than 1 year. And then I say, what's the chance of surviving 2 years? And the answer is 30%. Does anyone see a problem with this? We don't have zombies, right? If you're dead, you stay dead, right? That's sort of the way the world, at least in Edmonton, I don't know about your place, but so this could allow zombies. You could have inconsistent events. You can have probabilities that don't make sense, that aren't meaningful. And also you want to have like an open set of times. You know, I said 3 months and 5 years, but I may care about 10 years also, just to make fine decisions. So I want an open set, be able to visualize it as well. So again, I want to rule this out also. That's too bad. So we need a different model. And so I already suggested a model. Build a patient-specific curve. So for this patient, I want to make sure that 95% at 3 months, 95%, yep. At 5 years, I want 85%, yep, counts. And maybe other statistics also. Yeah, good, this guy counts. How about this guy? Well, the 3 month was fine, even the 1 year, but the 5 year, this is way below 85%. Not him, and not this person either, because he fails all the different measures. Of course, over multiple, if I have many individuals, I could build individual curves and say which ones of these qualify to be waitlisted for the liver transplant. Okay. It turns out I did so in a paper recently where, where we decided to try to analyze the space of survival analysis and survival prediction systems. And I realized there's this interesting splits. Some tools produce risk scores. Some do risk scores, some do probabilities. And some, for example, do risk scores for a single time point, or maybe there's risk scores for multiple time points. Some do probabilities for a single time point. Another degree of freedom is, are you looking at for an individual or for a population? And this 2 by 3 by 2 thing is populated. There's Framingham study, which gives like a 10-year survival probability, or the Gale model for breast cancer. There are other tools which give group-based risk scores for one time. There's the SEER system, the Kaplan-Meier systems, which give a probability with infinite number of time points for the whole continuum. But then for a population, what I care about is right there. I want to do something for a probability, not a risk, give me multiple time points that I care about, and do it for an individual, not for a group. So I'm going to go there. So that's one question. What's the space look like and where do we fit in? Another question, how do I evaluate these models? There's something called concordance, which is used for risk scores that say, if you give me a pair of individuals, the person with the higher risk score should die before the one with the lower risk score. You get a point, otherwise you don't get a point. And again, that's not useful here because I don't have risk scores, I have probabilities and not a single point. So the concordance, C index is the wrong measure. There's a calibration measure. I'm going to call it one calibration, which for a single time point. And again, this is saying, if I say that the chance of surviving 1 year is 80% for 10 patients, 8 of them for 1 year. Again, I'll give more details about both these later on, but just it's worth saying that they both are just the wrong measures to look at. So we need another evaluation. We want an evaluation that says whether the model we're producing for this range of time values is actually a meaningful, important thing to look at. So how do you evaluate this model given this criteria? Well, I'm going to talk about, I want something to be distribution calibrated, decalibrated. Whenever I say there's a 95% chance of living 3 months, I want a 95% chance a patient will live 3 months. I want to be able to just read up what this says and actually do justice to these claims. So how do I do that? So that's what our task wants to do. So I gave you 2 problems. One is, how do I build these sort of individual survival curves, and how do I evaluate? Those are the next 2 topics for my presentation. How do I build this multitasking just regression model, and how do I evaluate? Let's talk about this. So imagine I have a random variable, which is the survival time, the actual time. This isn't time of living at least as long. This is the chance of dying at an individual time. So I can build a PDF, a probability distribution function, looks like this, for example. And now the question I had, which was the chance of living at least a certain length. Sorry, I think Sunmi's mic is on. So the chance of living this long, which is okay. And so the chance of living at least 4 years is just the integral from there over. It's just that integral. Okay. Well, I can discretize it. I can just say build a probability mass function rather than a probability distribution function, and look at, for example, here's 4 different chunks of time. And now the chance of living at least 4 years is just the sum of these 2 blocks, a chance of living between 4 to 6 years and a chance of living from 6 to 8 years. Okay. So there should be no surprise. I'm just approximating the integral by just discrete units. So in general, I can discretize it. The intervals don't have to be the same time. There can be an interval of 2 years and 2.5 years and 2.5 years, and that's a coincidence. 2 years again, and so forth. And then chance of 4.5 years is just the sum of these things. And if I define the chances of the survival of chance of dying in the kth interval, call it d sub k, the chance of dying in the kth interval. In this interval, that one or that one or that one, and so forth. So we can do all that. So I'm going to build a model for doing that. And just to observe quickly that if I had this probability mass function, I can just add them up in the wrong order. And again, I'm just going to do, this is sort of a proof by PowerPoint, right? You can just see quickly that if I add them up the wrong way, I'm going to get something like the survival curve. Okay. So it looks like this. It's blocky. I then just smooth it out, and I get the survival. And I get the survival curve. Okay. So again, if that made sense, great. If not, I'm just adding up the probability mass function in the wrong way to get the survival curve, and then smoothing it. So how do I do it? The multitask logistic regression model is basically just saying, I've got 4 intervals. So I'm going to build one logistic regression-ish model for every time. So here there's m equals 4 time points. There's R variable, R covariates. I built some logistic regression, and I learned these different models, and then have to normalize it. The actual algorithm is in dk is the event of dying in the kth interval, and I have parameters for each of the m time points, each of the m intervals. I define the logistic regression-ish covariates, and then I'm going to talk about something like the unnormalized probability. Looks like this. I'm going to be a little bit sneaky. Instead of transferring the kth interval being just the logistic regression model with those k terms, I'm just going to be a little bit sneaky, which I'm going to actually add it from k to the end. It's still, I just have a bunch of parameters, the same set of m times k plus 1, m times r plus 1 parameters, and that gives me the chance of an unnormalized probability. I then build a partition function, which I want to make sure that when I add up the chance of dying, it adds up to only 1. So I got to normalize it by dividing by a partition function. People know about conditional random fields. Say, oh, Russ, you're in trouble because the partition function, I got like a 2 to the m different possibilities. Nope, no zombies. I only have to look at m terms as I compute this because there's only k different time points that can die. So I'll show that a bit later on. So this is convenient. Probability of dying is just the normalized version. Just divide by the partition function. And this will be a legal probabilities between 0 and 1, it adds up to 1, and so forth. The optimization function is this obvious term here. There's a log likelihood term. There's the L2 regularizer to make sure that the parameters are regularized. And there's a smoothness criteria that says the chance of dying in time 3 is like the chance of dying in time 4. Well, remember that little trick about summing them up. That little trick means I don't need this term. I get smoothness. If I do regularization, smoothness comes automatically, which is really cute. Okay. It's convex and differentiatable. You initialize the parameters by using uncensored data first. There's a quick optimization. Then use EM or something, or all of these data being censored. You can find C2, the only one parameter, this way it doesn't matter anymore, using cross-validation. And how many time points? Well, we chose m time points, square root of n number of instances. And we try to fix them to be the same number of events per time point. Lots of details, but read the paper. For a novel patient, the game now is, here's a novel patient. We have this model that's learned with these k plus 1 times m parameters. Given this model, we have a predictor, which is a survival curve for this individual. How do I get this? Well, there's a learning algorithm that takes survival data, right, which has a censor bit, and returns and computes this. What are the benefits for MTLR? Well, it handles censor patient naturally. I'm building a probability function. If I don't know something, I just have to sum it out. I integrate, I marginalize it. So if I have a censor point, if someone was censored at this time, I know this person's alive at time 1 and time 2. Well, maybe he died immediately after that. This is one possibility. He's dead, he stays dead. Maybe he's alive at time interval 3 and then he dies. Or maybe he's alive to the very end. Only 3 possibilities. I don't look at all the cross combinations. That's really nice. So it's very easy to handle censor data. And by the way, I can also do left sensor and interval sensor using the same idea. It's pretty natural. There's a simple estimation procedure. I already mentioned this. To find the median, I once had this. Median is when it crosses 0.5. Another interesting comment is I can also give like error bars and say the chance, there's a 50% chance of dying between 20 and 71 months by just looking at this probability interval. Another cute trick is what is the expected value? What is the mean value? And if you think about it, that's exactly this formula. It turns out this is, if you just look at the squint this for a moment, you realize that it's actually the integral of the survival curve is a mean time. This is not a new result, but it's kind of cute. So I get the mean time for people easily as well. This is cute. Okay, so all that works. Another thing, but gee, Russ, I know about Cox proportional hazard. There's the calibration prejudice estimator. I can estimate the chance of dying given time, and I get curves like this. So I can actually build survival curves from Cox by using this extension. Cool. But look at these curves. It's all the same bloody curve, just scaled out. With this MLTR model, the curves will cross. I'm integrating the patient properties and the time in a way that's coherent, that makes sense, and gives curves which give more information than just that same shape. Okay. So I spent a long time talking about the foundations. Let me talk about how to evaluate these guys. Are there questions at this point? Okay, I'll keep going. So I got a bunch of curves. They all do something. Each question, what do you do with it? Can you trust it? Can I tell a patient, this is your curve, and have that be meaningful to this patient? So let me talk about what it means to be meaningful by starting with a simple model. There's our friend Kaplan-Meier. There's Kaplan-Meier for the entire data set. And now I can say, it's the same distribution for every patient. And I can say, what's the median survival time? It's 20. That's where it crosses 0.5. So median is 20 months. That's a chance. And now this is based on, okay. So imagine I built this model with some data. I've got a new data set, 100 patients come through. If this model is right, how many patients should die before 20 months? All of them? 2/3 of them? Half of them? Any thoughts? I hate COVID. I can't see the audience. Any suggestions? If this is a meaningful model, if the median survival time is 50%, median means half will die before then, right? I see no one shaking their head because I don't see any heads at all, but I'm assuming people are accepting that. If 100 novel patients, 50 should die before the median time and 50 after. So to be more precise, if d-sub-i is the chance that each patient died, 100 patients, they should die 50 here and 50 there. Okay. And now to think about it is the number of patients for which the probability of that patient dying is greater than 0.5. All these patients are over here. That should be about 0.5. Okay, so that's what it means. Okay, well that was for median time. What about how many patients should die before the 75%? Well, it's 8 months. 75% should live at least as long term. 75% should be over here. And how about for 25%? 25% should die after this time. So basically the formula is for any row, I expect the number of patients should look for whom the probability, the Kaplan-Meier probability of death, that patient being greater than rho, should look like rho. And if you squint this for a second, what this is saying is the probability of death for these patients should be uniform. It should be same number of patients, 25% here, 25% there, and so forth. Well, that was great. That's Kaplan-Meier, one curve for everybody. What about this mess, where it's got different curves for different people? So here's 4 different people. Everyone has their own individual time of dying. Individual curves, and hence individual median survival times. So again, I build this model. I then take 100 patients I wasn't trained on. How many of these patients should die before their respective median times? Same argument. I expect 2 of these 4 patients should die. Oh, so perhaps this one and that one. This patient should die before 33.1. This patient should die before 7.4. And these 2 should die after 30 and after 49. So the formula is like this. There's individual survival, median survival times. And so I have the same basic formula, just with not Kaplan-Meier, but by individual probabilities there. And again, just to compare the formulas, they're the same. It's just here's individual survival. And once again, there's nothing special about 0.5. The same thing, 75% should die after this time and 25 after that time. So same basic formula, different claim. The probability of death, the ith probability function, the ith survival probability for the ith patient, the chance that the ith patient dies, given that patient's individual survival curve, should be uniform. Okay, so I'm just doing the same thing over here. So I'm going to talk about decalibrated to mean this thing, this quantity is uniform in 0, 1, the same way it was without the sub-I for Kaplan-Meier. So what does that mean? So here's a patient, and this patient actually died at this point here. This patient was died. If this is a histogram turned sideways, this patient actually died died in the first quadrant. And this patient, different patient, of course, but this patient died in the third quadrant. And this one in the much different curve, but this patient died at a later time, but that's only the second quadrant for this patient, and so forth. So out of the 4 patients, 1 out of 4 died at each one of these quadrants. This would be calibrated the way I want. And now, again, this patient here, now imagine I had not 4, but 2,402 patients. Well, if I'm looking at not 4, but 20 different bins, I expect them all to be about 0.5, 0.05, 1/20th. And so again, I'm running out of time, a little bit faster, just so about uniform things. We can talk about these numbers, these based on 5-fold cross validation, yada, yada. We can then do like a chi-square test to see, did this distribution look like it's 0.5? And there's some statistics to say whether it was calibrated or not, decalibrated. And what about censored patients? If you think about this Bayesian net for how the dependencies work, you can say they're independent. I'm going to skip the details, but you basically just blur out a patient who died in this interval. That patient who was censored gets blurred out over the remaining probabilities. It gets 1/6 in each one of these bins, and you add them all up and you get these Russ, all that stuff. So I've got about 5 minutes. I'm going to whiz through sort of the empirical study we did. So you remember I'm looking at just probabilities rather than risks, infinite number, an arbitrary number of data points rather than just one. And I'm going to actually look at both Kaplan-Meier as well as individual survival distributions for some of these analyses. So individual survival distribution, we looked at MLTR. There's something called accelerated failure time with the Weibull measure. I mentioned Cox with the Cambridge-Prentice one. There's the elastic net extension to Cox, finding high dimensional data with Cambridge-Prentice as well. There's also random survival forest, another tool of Kaplan-Meier, as well as Kaplan-Meier. And you can see the curves, and you can see the accelerated time, and what Kaplan-Meier's one thing, one's curve. The Cox is just sort of scaled up, and even with the EM, it's a little smoother here with the EN, a little smoother, but same basic shape. There's RSF and MLTR, which the curves can cross. So we looked at a bunch of data sets. We found 45 publicly available data sets. We looked at 8 for variety. And again, I'll skip the details, but looked at the number of instances, number of sensor values, how many features they had. I want to have the number of instances range from 170 to 2,402. The percentage of censoring was 17% to 86%. Number of features was 12 to 71. We thought we'd do some post-processing, some pre-processing features, and we end up with a small number of features. So 6 to 2,000 features to when all was said and done. Okay. We talked about different categories, sort of nice things, which have a small percentage of centering and have relatively large number of instances per feature. There's also high centering things, which have lots of centering, and high dimensional things. Okay. We tried it out, what were decalibrated. Cox didn't always converge, but we used the EN version of it. We put it in bold. I'm not sure you can quite see it, but it turns out MLTR was decalibrated for all 8 data sets, but so is Kaplan-Meier. And in fact, we've proven in our paper that Kaplan-Meier is asymptotically decalibrated. So it's not too surprising that it would win all 8 times, but it's not individualized. And other tools did fairly well here. Again, I want to argue that to build a useful model, it should be individual, telling patients what happens to him or her. It should work for multiple time points, the challenge I looked at, but also should be decalibrated. So when you say there's a 70% chance of dying, that is a curve, if you look at where 0.7 is, you should say there's 7% chance of dying at this time, and have that being a meaningful statistic, and decalibrated means it is. Okay. Other models, so again, I want these things to happen. Okay. Oh, okay. So decalibration is also concordance, or C index, 1 calibrated, L1 lost, and so forth. We also did Breyer score. I'm going to skip that here. What is concordance? So imagine this is the predicted score, something called MELD score for people who are hepatologists. That's a measure of how long someone survives with end-stage liver failure. And this is a pretty good estimator, but imagine I use that here for deciding the time of death for patients who have a liver. It wasn't designed for that. You can imagine we had these scores, and then we actually saw what order the patients died in. And it turns out this patient was the first to die, this was the second, and so forth. How good is this? What's the C index? Well, for patient 1, 1 died before 2, so he gets a point. This measure gets a point. 1 did not die before 3, so it doesn't get a point. 1 died before 4, and 1 died before 5. So that's for this point. If I go down to 2, 2 died before 4 and 5, 3 died before 4 and 5, and 4 did not die before 5. So out of the 10 different combinations, this measure, this score was right 1, 2, 3, 4, 5, 6, 7, 7 out of 10 times. That's what the C index is. And there's usually with ties and with sensor data, that's it basically. It's a risk score, it's a number, not probability, but you can still take MLTR and use the mean time and get a measure for that. We can see how well these different measures worked here for concordance. Blue means it did the best of all the different measures. Forget Kaplan-Meier, that's not meaningful, same curve for everybody. And we can see that MLTR did the best for 6 out of 8 times. And times it wasn't the best, it wasn't far off. There's also one calibration. This is the Weatherman problem. Every day the Weatherman says a chance of rain tomorrow. He says 60% chance of rain tomorrow. Imagine he does this, if he did this 5 times, do you expect it to rain all 5 times? No, that's not what calibrated means. If he says 60% chance of rain tomorrow on 5 different dates, you expect it to rain 3 of those 5 times. And that's what one calibration means. And we can talk about this measure here. So look at, for example, the 30-month, and you can now say, let's look at 3 different bins. For these bins, the average of these 5 numbers is 0.78. And we actually found 4 out of those 5 patients actually died before here. And the same for the second cluster, 45%, and 3 out of 5 died there, and so forth. So you want these numbers to look like each other. And again, you can use the Hosmer-Levenshaw criteria for looking at that. I'm running out of time, so let me just say that once again, we did comparisons for different data sets at the 10%, 25% percentile, and so forth. And we found that MLTR did really well there. Okay. I'm going to skip L1 loss. I'm running out of time, but there's a lot of issues making this work right. And maybe just again, we did fairly well there, although even the best was crappy. So we can give advice to people if you care about depending on your data set size and what you care about, whether you care about calibration or discrimination, what to use, and you can see MLTR did very well on this. So it's a paper that appeared last year in JMLR. We actually used it for the task I mentioned about predicting transplant survival for PSC. And we can say this patient probably should be waitlisted and this patient should not. And that appeared 3 years ago. I'm going to skip all the way down here. There's a lot of interesting future work and just go to the conclusions. We have a website you can go to, put your data in and play with it, and tweak different things about different types of regularization and different types of ways to do pre-processing and so forth. There's also a Github Repository, which has some R code for this. I want to just acknowledge that I'm a machine learning person. I got to work with world-class liver transplant specialists, as well as other people for other studies. Contributions, I build an individual survival distribution that is a general approach for survival prediction that encompasses many standard tasks. We introduce a new evaluation measure. We described a particular model in this context, which does very well in terms of this measure as others. And we looked at it was effective, and this website to go to. Maybe I'll end here and just say that, do you guys know who Steve Wright is?
No.
You know Steve Wright? Okay, well, he's a comedian. So I like his quote, right? I tend to live forever, so far so good. I will end here, and I apologize for going over other questions.
Whoa, take a breath, Russ. That was a lot of information. I'm sure there are a lot of questions. I'm going to tell you this. I thought this was very, very exciting. I'm in my field. We do lots of time to event probability estimation, and the problem with the Cox model, as you say, is that it assumes a baseline hazard function, and all you can do is play around with that baseline hazard function. So this obviously gets way beyond that. I'll jump in with one quick question, that is, and I didn't hear how you actually discretize time, whether that's data-driven or whether that's an arbitrary choice, and what that does to data requirements, because you're doing piecewise fitting with these models. Do you retain the same data requirements because you're spreading it out to the same data over time, or do you have a big jump up in data requirement?
Great question. So what we do is we look at all the, just look at the labels, not the data. Oh, in 5-fold cross-validation, we look at the training set. We look at all the events that happen, and we try to have the same number of events that happen in each of the other intervals. So if we have 100 individuals, we use square root at least 10 different time points, and we make them 10. So 10, to look at the events that happened, we take the first, sort them, take the first 10. The endpoint of that is the first interval, and then the next 10 and so forth. I should mention that there's another GitHub repository that copied our code, which is fine, it's public. They then did the wrong thing. They took, if it's a 5-year interval, they took 1/10 of 5 years. And so some of these intervals will have 0 events in them, and some will have 40% events, which is a really bad idea. That doesn't work at all. So that was the first question. It does make a difference. If you do it wrong, you get very bad answers. But this idea of actually looking at equal number of events per interval worked well. And squared event, that's a heuristic. You can try 10, you can try 100, you can try that. That seems to work well for all the results we gave were all based on that.
And data requirements are preserved or increased?
Well, what do you mean by data requirements?
If you want to get if I have a fixed population size, do I get a robust model using this versus any of the other methods, or does this more have larger data requirements because of the fitting of multiple models for each time interval?
We do have regularization to helps a little bit. We try to have a wide variety. Obviously, with low amounts of data, you'll get crap, and we found that could happen. We looked at 45 data sets, and we seem to do the best. I should mention the best is not necessarily that good. Right? You're in medicine, you know that you need C index greater than 0.8 to be useful. Well, whatever. I should point out that just even C index, why did it require that for things that make no sense for? So question 1, what does it mean to be good? I gave you 5 different evaluation functions. they all are wrong, including decalibration. I can tell you why decalibration is a bad idea. They're wrong in different ways. So question one, what does it mean to be a good model? How do you evaluate that? And I don't have an answer to that. Second question is, how much data do you need to have this happen? Well, what does the word need mean, right? At what point is it a publication? Well, whatever. At what point is it clinically relevant? Depends on task. The tool we designed for looking at PSC liver transplants, again, this is for waitlisting them. The clinicians in Edmonton are using that to augment their decision of who should be waitlisted or not. Does it work perfectly? No. Is it better than just getting a gut feel? They think it is, and they're using it. It's been published, and a few other people have asked me for the code base, so I think other people are using it as well.
Russ, I'm not sure if you saw, there's a question also from Piotr Slomka. He's asking about MLTR versus other AI approaches like deep hit. Not sure if you are familiar with that.
I know Mihaela. So I just organized a symposium on survival prediction, and Mihaela Vandershaw, who did deep hit, is one of my one of the other co-organizers. yeah, we did try many neural net based models. So again, you're building an MTLR, you're building a probability mass function, and I have to populate them, I have to give I use something like logistic regression. You can put a deep net there. And Mihaela did something a little bit different than that. But yes, we did compare them. MTLR worked a little bit better. This was 2 years ago. I know Mihaela's been advancing some of the deep hit work. So now it's perhaps better. But we did compare it with those tools. It didn't seem to be any advantage. You also asked about AUC. So AUC obviously, so first, C-index is the first cousin of AUC. They both are looking at sort of number of mismatches. AUC obviously is for binary decisions. So if you're making a binary decision, you have to figure out what point you're looking at.
So I think, so if I could comment a little, so basically we always come up with this, we like to get AUC and because we may not care exactly where the patient dies, but knowing the time would maybe help us. So is it possible to get AUC at a specific time period, for example, from this, and perhaps better than with AI approaches, which is just binary?
Yeah, you're giving a probability, so AUC is well defined. But that corresponds to, that's like a time-dependent C-index, because it's just exactly the point. There's a question of what you do with sensor data. And so clearly, if someone was censored after that, we know about them. What about the people censored before? You just ignore them? Well, yeah, you could. There's a lot of other tricks. I prefer using, if you're going to look at 1 year time, and I don't like AUC. It doesn't make sense when you really think about it. Yes, there are imbalanced data. There's other ways to handle it. But one thing you could look at is the one calibration. At time of death, I have at 1 year, I've got people have a probability of death. I can ask questions like, what's the chance of the one calibration I mentioned, of the people who I gave 90% chance of dying, did 9 out of 10 of those people die in that interval? So I think if you're going to look at a single time point, I want to advocate using one calibration for that and not AUC, because I'm not sure what AUC is really doing. And I think I've talked to many clinicians. I've yet to talk to any clinician ever who knows what AUC is, except it's a measure between 0 and 1 in a straight line. And it's this curve here, and 0.5 means random and 1 means good. It's actually doing what C-index is doing. It's just looking at the number of times I predict a lower number and it gets inverted. But they don't know that. They just use it. So I didn't mean to dump on clinicians. They're brilliant people. I enjoy working with them, but they all follow the rules. You have to use calibrate. You have to use Cox. You have to use C-index to measure it, even though it makes no sense because. So back to your question. If you want to look for a single time point, you could discretize it and look at that. You can now use AUC, which corresponds to C-index. I would advocate instead saying, I've got meaningful probabilities. I can now use decision theory to decide what to do, what are the outcomes by making different decisions here. So I would recommend using one calibration to see what's calibrated. And if it's calibrated, now I know that when I say 0.9, it means something. When I say 0.7.
Thanks. Russ, one quick question. It's Conrad Pi asked, and I was going to ask it as well. Competing events such as competing mortality? That's quite relevant to obviously the scenario you presented. Have you applied that?
Great question. Some of the slides I skipped talked about that. Competing risk for people who don't know is when multiple things could happen. In the easy case, when you get hit by a bus or you die of liver cancer, they're independent and you can just build simple ways to look at them. DPIP does that. What are those correlations between them? So we had exactly this problem. I told you about the chance of someone surviving given a liver transplant. We want to also look at the chance of surviving without a transplant. So the SRTR data set has tens of thousands, 100,000 individuals and has time when they were waitlisted. And some patients on the waitlist die in the waitlist. Good. Some leave the study. That's fine. Some get a liver. Okay. So that's a censoring event. Wrong. That little Bayesian net I showed quickly that shows independence, that's wrong. The person who gets, people are waitlisted, some gets them. The person who has the highest chance of dying gets the liver. That means the chance I got the liver is correlated with time of dying, which means the standard model that says centrally independent is wrong. So we're looking at various copulas. There's, I forgot the copula. So yeah, we're looking at a model that actually incorporates copulas. We can't get into MLTR, we're using RSF for that. But great question. Obviously, you've thought about some of these things. Yeah, no one has answers, counterfactual. What would have happened if, and you're going to make up a guess, and copulas are these ways of guessing. Thanks a great question.
Okay, and I think with that, we are right at the top of the hour, just passed. And I want, on behalf of everybody, to thank you for a stimulating, very exciting lecture. Looking forward to reading some of the work and seeing more coming out on this. Thanks
Thank you
again.
very much for enjoying it. I have a website that sort of summarizes many of the stuff, and I'll send it to Bill to send to the rest of the community. People are interested.
Perfect.
That's actually a QR code there if you want to scan that in.
Okay.
Thanks, everyone.